Good morning, everyone. Today, we're diving into the exciting world of sorting algorithms, where cutting-edge technology meets the age-old challenge of organizing data efficiently. Imagine a massive library, books scattered everywhere, and your task is to put them in order. That's where sorting algorithms comes in. They're like a super smart librarians efficiently arranging data for quick retrieval. These algorithms play a crucial role in computer science, speeding up how programs handle information. For years, computer scientists have been designing and improving sorting algorithms. However, as datasets grow larger and algorithms become more complex, squeezing out even better performance gets trickier. But fear not, guys, for a revolutionary approach has emerged: DeepMind's AlphaDev. This game changer uses deep reinforcement learning, or DRL, to automatically discover entirely new sorting algorithms. It's like having a curious and relentless AI assistant that never stops exploring, experimenting, and learning. Now, get ready for a thrilling showdown. We'll dive into the world of optimized variations of DeepMind's AlphaDev sorting algorithms, comparing three specific contenders. First, the original AlphaDev's paper, the trailblazer that started it all. Second, faster sorting algorithms beyond DeepMind's AlphaDevs. These challengers use mimicry to refine AlphaDev's results. Third, shorter and faster than a short tree AlphaDevs, a daring contender challenging AlphaDev's claims of the shortest programs for sorting tree elements. We'll explore the strengths and weaknesses of each variation, uncover trade-offs and best practices, and witness the clash between AI-driven approaches and human-guided methods. But wait, there's more. Beyond just sorting algorithms, we'll uncover insights into the capabilities and limitations of DRL for algorithms discovery in general. This knowledge could be invaluable, potentially informing the developments of AI techniques for discovering efficient solutions in various computational domains. So, let's dive in and witness the future of algorithms optimization unfold.
Okay, let's take a deeper dive into the world of sorting algorithms, specifically comparing the advances made beyond DeepMind's AlphaDev. Today, we'll look at two key supplementary papers that take sorting efficiency to the new heights. So first, let's introduce the papers. The first paper is titled Faster Sorting Beyond DeepMind's AlphaDev by Mimicry, which builds on AlphaDev's foundation to uncover more efficient sorting algorithms. The second paper is Shorter and Faster Than Sort Tree AlphaDev, which challenges AlphaDev's claim about the shortest implementation for sorting three numbers. So, in Faster Sorting Beyond DeepMind's AlphaDev, the authors used mimicry to refine AlphaDev's algorithms. They found shorter and faster code sequences, like a sort tree algorithm using SIMD instructions with just 9 lines of code, significantly less than AlphaDev's 17 lines. This led to a speed improvement up to 41% for sort 3 and 69% for sort 4. They also explored a wider range of CPU instructions, including AVX2, AVX, and SSE, achieving substantial speedups. Using these instructions, they compared multiple values simultaneously, enhancing data movement efficiency. The combination of human creativity and AI tools was crucial. Human insights helped invent new algorithm designs and optimize translations to hardware and complementing AlphaDev's AI-driven search. This synergy of human and AI efforts significantly boosted sorting performance. Now, let's delve into the second paper, Shorter and Faster Than Sort 3 AlphaDev by Dr. Cassioneri. Their work disproves AlphaDev's claim that no shorter than 17 instructions sort 3 program exists. Neri presents sort 314 and sort 315, which uses 14 and 15 instructions respectively, outperforming sort 3 AlphaDev in runtime benchmarks up to 29%. Neri's sort 314 uses a loop to reduce instruction count, while sort 315 employs a branchless approach inspired by sorting networks. Both are more compact than AlphaDev's sort 3. So, what makes AlphaDev's algorithm so special? AlphaDev's algorithms were discovered through trial and error, reinforced learning, and without prior human knowledge or guidance. This led to novel solutions using bit manipulation and low-level CPU instructions in unique ways.
In this part, we will take a closer look at how AlphaDev stacks up against its optimized versions and chat about where AI-driven algorithm design might be headed. So we put these algorithms through their paces using different sorting benchmarks, data sizes, and computer setups. Turns out, the tweaked versions from paper 1 were pretty speedy, beating AlphaDev by up to 41% for sort 3 and 69% for sort 4. Paper 2's sort 3 was no slouch either, outperforming AlphaDev by 6% to 29%. But why did these optimized versions perform so well? It all comes down to a few key factors. AlphaDev's DRL approach is great at exploring lots of sorting methods, but it might not be as focused as the human-guided strategies in Paper 1 or Paper 2's laser focus on sort tree. Plus, Paper 1's mimicry tricks were awesome at shrinking code and boosting speed, while Paper 2's design choices like using loops and lookup tables made it super efficient. But there's always a give and take, right? We noticed that code length and execution speed don't always go hand in hand. AlphaDev liked to skip branches for speed, while Paper 1 tried to balance code size and speed. Paper 2's sort tree was all about keeping things compact. So depending on what you need, you might prioritize speed, strike a balance, or even fine-tune for specific hardware. And let's not forget about hardware compatibility. AlphaDev's DRL discovered methods might be more adaptable to different hardware, but Paper 1 tweaks were tailored for x86, 64 CPUs and SIMD instructions, which of course could limit their portability. To get the best of both worlds, you might need to develop hardware-agnostic design principles, or you use conditional code paths that adapt to different hardware. Now, AlphaDev's DRL approach was pretty nifty at finding efficient sorting methods all on its own. But it's not perfect. There could be biases, and it's not always easy to incorporate human know-how. That's where Paper 1's human-guided approaches come in, showing how human expertise can lead to sorted code and serious speedups. Imagine if we could combine the best of both worlds, the raw power of DRL with the finesse of human expertise. It could lead to some seriously efficient and versatile sorting solutions. Human intuition could guide the DRL process, help design better reward functions, and refine the algorithms that the AI discovers. To give you a taste of what AlphaDev can do, we threw a curveball at it. Sorting a list of student names with different lengths, you'll have to deal with variable length strings and consider both length and alphabetical order. And for some training, it might come up with a custom sorting method using tricks like bucket sort or radix sort.
Okay, before we finish up, let's quickly go over the key things we found when comparing the original AlphaDev sorting algorithms to their optimized versions. First, the optimized ones were a lot faster and more efficient. For example, the optimized color version of sort tree was almost 7 times faster on average. Even more impressive, the SIMD optimized sort for was up to 10 times faster on certain computer systems. The SIMD optimizations using pack instructions really helped improve sorting speed, especially on non-Zen Plus CPUs. However, SIMD also had some trades-offs. The added complex instructions and performance changing across different systems is something to think about, like the SIMD sort tree only running 5 times faster on Zen Plus while doing much better elsewhere. On the other hand, the scalar optimizations were a little slower than SIMD overall, but provided more consistent speed improvement across different systems. So in situations where maximum speed isn't the most important thing, these scalar tweaks could be a good middle options. Overall, the optimized algorithms showed the big potential of using AI techniques like deep reinforcement learning to discover and fine-tune algorithms, but our analysis also pointed out some pros and cons of different optimizations approaches that needs to be considered based on the specific use case. Those impressive speed gains but also trade-offs really highlight how much more can still be done in this exciting area of using AI to design and optimize algorithms, which leads perfectly to my colleague Samuel, who will walk through some fascinating future research directions in this field. Samuel, the floor is yours.
So what's next for AI-driven algorithm design? There's loads to explore, like finding smarter ways for DRL to explore, mixing in human expertise with AI approaches, or even applying AI to all sorts of algorithmic challenges not just sorting. The trick is to keep pushing the envelope and mixing things up to discover some really game-changing algorithms. And that's a wrap for our collaborative comparative analysis and discussions of AlphaDev and its optimized versions. Now for the next chapter, we will geek out even more about the exciting work of AI-driven algorithm design.
While Dr. Nair's solutions provide improvements, AlphaDev's breakthrough lies in its ability to autonomously derive efficient and non-intuitive algorithms. This demonstrates the powerful potential in AI algorithm innovation, paving the way for future breakthroughs in sorting and beyond. Thank you for joining me in this comparative analysis. I will have my colleague take the spotlight for the next stage.